Hello, Math 1224. This is Dr. P with Lesson Supplement 405. This is about Nicoles' awesome method for finding partial fraction coefficients. So, about a week ago, in her response to one of the lesson launch videos, Nicole mentioned that she knew of an easier way of finding partial fraction coefficients than the one that I had shown in my previous video. So, I'm familiar with the method she was referring to, and wanted to create a video so that I could share her method with you so that you can do some of these problems more efficiently yourself. So I've put a rational function here. You'll notice it's already in the form where the numerator's degree is smaller than the denominator's degree. So this is just about ready to decompose into partial fractions. I need to go ahead and rewrite this so that the denominator is in factored form. So the denominator is 2x plus 1 times x plus 1. And I know that the partial fraction decomposition will be something of the form a over 2x plus 1 plus b over x plus 1. Okay, now Nicoles' method begins in the same way that the other method begins, which is by writing these two things as equivalent, these two rational functions, 7x plus 1 over 2x plus 1, x plus 1. That's equivalent to, once we choose the right values of a and b, this will be equivalent to a over 2x plus 1 plus b over x plus 1. And then we multiply the entire identity through by this denominator here, this one. And that gives us 7x plus 1 equals a times x plus 1 plus b times 2x plus 1. Now, here is where Nicoles' method diverges from mine somewhat. The way that I would have solved this problem would have been to match coefficients. So realize that there's a linear coefficient over here of 7, and there's a linear coefficient over here of a plus 2b. And then set a plus 2b equal to 7, and then create another equation based on the fact that this constant 1 has to be equal to a, 1 times a, plus b, that's 1 times b, and I would get a plus b equals 1. And I could solve that system of equations and come up with appropriate values of a and b, and then I'd be done. Nicoles' method, though, is a little bit more straightforward. It doesn't require solving a system. It relies on using the fact that we know that this equation, new color, this equation must be true for all values of x. That equation needs to be true for all values of x. So I can pick values of x that are convenient for me, that might reveal some immediate and powerful truth about this equation. So what do I mean by reveal some immediate and powerful truth? What in the world does that mean? Well, what I mean is, I could, for example, say, let x equal to 1. Then this equation has to be true when x equals negative 1. So that means that the left side, that's 7 times negative 1 plus 1, that's negative 6, is equal to this, which you'll notice is 0 when x is negative 1, plus b times 2 times negative 1, that's negative 2, plus 1. So in other words, negative 1 times b has to equal negative 6, and therefore b has to equal 6. And we got that by choosing a value of x that was convenient for us, that knocked out this entire term of that equation. All right, so now we might try to choose some value of x that will knock out this term of the equation. That's a little bit trickier, but I think that x equals negative 1/2 will do it, so let's give it a go. Let's see here, there we go. What if we try x equals negative 1/2? Then we get the left side is negative 7/2 plus 1. I'll work out what that is in just a minute. Equals a times negative 1/2 plus 1. And then let's see, I can't delay this any longer. Negative 7/2 plus 1 is negative 5/2. And that has to equal a times 1/2. So I think if my mental arithmetic is right, that a is going to equal negative 5. Now the test of any of these things is to see whether it actually holds up when I substitute things back into this partial fraction decomposition here. So in other words, with those choices of a and b, Is this statement true? Well, let's check. Well, let's see. If a is negative 5 and b is 6, then I get negative 5 over 2x plus 1. This is the right side I'm computing. Plus 6 over x plus 1. And then adding those together, I have a quick method for doing that. It's just take this times this, and then this times this, and add those together. And then the product of the denominators is 2x plus 1, x plus 1. And I think things are looking pretty good for me right now. Yep, I like where this is going. Still got that 2x plus 1, x plus 1. And so I get 7x plus 1 over 2x plus 1, x plus 1, which is exactly what I wanted here. It's the same thing as, it's the same thing as this. So those coefficients check out. So just to summarize, Nicoles' method is, instead of setting up and solving this system here, I know I wrote this part, but I didn't need to write this part to do this important part down here. Instead, I use the fact that this equation is true for all values of x, and then I pick the values of x that I want to examine. X equals negative 1 because it knocks out this term, makes it 0, and x equals negative 1/2 because it makes this term 0. And when I make one of the terms 0, it makes the other one much easier to solve for. So anyway, that's Nicoles' method. However, I must issue a caution. Let's see, what would be a good color for a caution? I'm already using red. Let's just use gray. I don't know why gray is such a good color for caution, but anyway. Caution. This method doesn't always work. It doesn't always work, and in fact, you may not know when it's not working. Okay, which sounds awfully ominous, so I should explain exactly what I mean by that, because why would I give you a method to use that could deceive you into thinking it's producing correct results when it's producing wrong results? So what I really mean by that is this method will work as long as you have the correct partial fraction decomposition. Let me write this down. Okay, for the method to work, you need to have the right partial fraction decomposition. And the algebra has to work out. Now, when I say the algebra has to work out, what do I mean? Sometimes you might have the right partial fraction decomposition, but Nicoles' method just doesn't give you enough information to figure out what the coefficients are. So just as an example of that, let me give this rational function here. So let's try 2x minus 5 over x plus 1 squared. Okay, so a good partial fraction decomposition of that would be a over x plus 1 plus b over x plus 1 squared. Now remember, this is that weird case where you have a repeated factor in the denominator. It's a factor squared. So I need to have, in my partial fraction decomposition, I need to have a partial fraction where that factor is raised to the first power, and then one where it's raised to the second power. Okay, so anyway, let's see what happens when we try using Nicoles' method on this. If I multiply through by x plus 1 squared, I get 2x minus 5 equals a x plus 1 plus just plain b there. Okay, now I can get somewhere with this. I could say, since this equation has to be true for all values of x, this is for all x, I know, for example, that I could pick, let's say x equals negative 1 and get negative 2 minus 5 is negative 7. This term goes away, and I'm just left with b equals negative 7. So that's all well and good. But then if I want to find a using the same method, well, I'm kind of stuck. I know what b is, so I guess I have that going for me. But there's no easy value of x which knocks this term out. This is always going to be a negative 7. The good news is, because I know this is negative 7, I could just substitute that back into this and then use algebra or some other method. Like, for example, I could consider the fact that this has a linear term of 2x, so this has got to have a 2x, and the only place that x comes from is the ax. So a would have to be 2. So anyway, Nicoles' method sort of works. You just have to use some other algebra sense to get there. Now here's the more dangerous situation. Here's the one that you really have to look out for. Let's suppose I give you the following rational function. 3x squared plus 2 over x squared minus 1, x plus 3. Okay? And my partial fraction decomposition is a over x squared minus 1 plus b over x plus 3. All right? Then if I multiply through, I get 3x squared plus 2 equals a times x plus 3 plus b times x squared minus 1. So now if I pick strategic values of x, I will get, let's see, let's start by choosing x equals -3. Get that one out of the way. All right? If x is -3, then that left side's going to be 27 plus 2, that's 29, yuck, equals 0 plus b times 9 minus 1, that's 8. So 8b is 29. That makes b equal to 29 over 8. All right? Now, to knock out this term, I'm just going to pick a value of x. I'm going to pick x equal to 1. If I pick x equals 1, the left side is just 5. And the right side, that b term goes away entirely. I get 4a equals 5. So a is 5/4. So my partial fraction decomposition then is going to be, let's just write it over here. Should be 5/4, and then b should be 29/8. All right, now I'm going to zoom out, and we're going to do a little bit of algebra to check whether that works out. So here's my check. Is it true that 5/4 over x squared minus 1 plus 29/8 over x plus 3, is that true that that's equal to this? Let's find out. So if I do my little multiplication strategy here, I get 5/4 times x plus 3 plus 29/8 x squared minus 1 over that same denominator, x squared minus 1, x plus 3. And already I see that there's a problem here. I know it's not immediate to see it, but I'm looking for a 3x squared in the numerator, and this has no x squared in it. This has 29/8 x squared. Doesn't have a 3x squared. There's nothing here that would produce a 3x squared. Denominator is the same, so it's not a matter of this being equivalent to some other fraction, which is this. It's just, this is simply not equivalent. So Nicoles' method didn't work. Now, why didn't Nicoles' method work? The problem was actually right here. The problem was I chose the wrong partial fraction decomposition. You probably knew this already. Because this term here, this partial fraction here, because it has a quadratic in the denominator, first of all, I probably should have, now that I think about it, I probably should have factored that in x minus 1, x plus 1. That would have been a more honest way to do this. But it still makes my point for me. This partial fraction here should have had a linear in the numerator because the denominator is quadratic. And actually, even though this is not totally factored, and therefore this is not the standard method, if I put a linear here, I would have eventually gotten a working partial fraction decomposition. Would it have been easier to integrate? Who knows? I probably could have done better on this. But the point is, Nicoles' method won't tell us if we're doing something boneheaded, like using the wrong partial fraction decomposition. It will perfectly happily spit out coefficients, and the reason it does that is it's essentially saying, well, if there were coefficients, this is what they would be. But it's not saying that those actually do work. To check that they do work, we have to go back and do this check. Or at least we have to know that we are using exactly the right partial fraction decomposition, and that these coefficients are uniquely determined. Anyway, that's a bit of a subtlety there. But I don't want to scare you off of using this method. It's very good for situations where you have some number of linear factors and none of them are repeated. That's the best place to use it. So anyway, thank you, Nicole, for mentioning this method, and I hope the rest of you found this entertaining and or informative.